Hey everyone, and welcome to The Explainer. I am so thrilled to have you here today. If you've ever stopped to wonder how a quick tap on your phone magically pulls up a video from a server literally thousands of miles away, well, you're in the exact right place. Today we're unraveling the incredibly complex yet totally fascinating web of global connections that make our modern digital lives possible. We're going to break down the physical roads, the vehicles, and the traffic directors of the data that's swarming around us every single day.
All right, so let's dive right in. Welcome to Chapter 2, Communication and Networking Technologies. We'll be pulling our insights directly from the source material today. Our main goal here is to take all these foundational networking concepts and actually map them out visually so you can really get a sense of how our digital world is stitched together.
So here's our roadmap for this explainer. First, we'll look at the evolution of networks. Second, clients, servers, and peers. Third, network topologies explained. Fourth, wired versus wireless media. And finally, number 5, the Internet's infrastructure.
Kicking things off with Section 1, the evolution of networks, from mainframes to mobile. What's truly staggering about this whole evolution is just how fast things changed. Think about it. Back in the 1970s, it was all about these massive, room-sized mainframes. Users just accessed a central computer using super basic terminals. And big organizations started connecting these mainframes across thousands of kilometers using WANs or wide area networks. Then the 80s hit. Boom, the personal computer arrives. And suddenly people actually have machines sitting on their own desks. To share files and, honestly, to save some money on those really expensive printers, organizations started linking these PCs together inside single rooms or buildings. And that's how we got local area networks, or LANs. Fast forward to the 1990s, and we enter the modern era with internetworking, literally connecting those LANs to WANs and ultimately to the global internet. And then, of course, the 2000s untethered us completely. Mobile devices and wireless networking went mainstream. So in just a few short decades, we went from needing a dedicated desk terminal just to type something to having the entire globe's network right in our pockets. Pretty wild.
Moving on to Section 2, clients, servers, and peers, how devices interact.
So let's compare the two dominant ways that devices actually interact with each other. First up, we've got the client-server model. You can kind of think of this like a restaurant. The central server is the kitchen, it provides the apps or the files, and your computer is the client, sitting out at a table just placing an order. Because everything is coming from one central point, organizations can easily control who accesses what, and they can run really robust antivirus software to keep malware out. But then, on the flip side, we have the peer-to-peer model. This is a totally decentralized setup. So instead of a kitchen and diners, it's more like a potluck. Every single computer on the network acts as both a client requesting files and a server that provides them. The really brilliant thing here is that peer-to-peer avoids network congestion. If 50 people want to download a file, they aren't all just hammering one single server. They're actually downloading different pieces of that file from each other, all at the exact same time.
Now, let's drill down into that client-server model for a second, because clients actually come in two distinct flavors. First up is the thin client. A thin client relies almost completely on the server. Literally, all it does is send your input, your keyboard strokes or mouse clicks, straight to the server, and then it just receives and displays the output. All the heavy lifting, the actual running of the application happens entirely out there on that remote server.
And you can contrast that immediately with a thick client. A thick client actually handles at least some of the processing locally right on your device. It might download the app entirely and run it itself, and then just use the server mostly to fetch updated data. So an easy way to remember it, thin means highly dependent, thick means highly independent.
Next up is Section 3, network topologies explained, the roadmaps of data.
Topology is really just a fancy word for the physical configuration of a network. Think of them as roadmaps. First, point-to-point. This is the simplest one out there, just a single dedicated road directly linking two systems together. Next is the bus topology. Picture one long shared highway, where every device has a little driveway connecting to it. If a message gets sent, it travels all the way down that shared highway and basically broadcasts to everyone, though only the actual intended recipient processes it. Then we have the star topology. Now this one is absolutely crucial because it's the most common way we configure local networks today. Every single device has its own dedicated link to a central switch, kind of radiating outward like a star. That central switch acts like a traffic cop, seamlessly directing all the communications and making it super easy to connect to the wider internet. Moving on, a mesh topology is the most robust setup. Every single device has a direct, dedicated link to literally every other device.
And finally, a hybrid network is, well, exactly what it sounds like. It's a collection of connected LANs that might mix and match all these different topologies just depending on what a specific organization needs.
All right, that brings us to Section 4, wired versus wireless media, the vehicles of data. When we talk about physical data transmission, we're talking about actual physical cables. Take the twisted pair cable, for example. This one uses copper wires that are literally twisted together to reduce interference, and it is the standard choice today for most high-speed local area networks and telephone lines. Then you have the coaxial cable. If you look at one, you'll notice a really thick metallic shield. That shield provides some heavy-duty protection against interference, which made it the historical go-to for cable TV and larger metropolitan area networks, even though it's definitely less common for your basic office networking nowadays.
When you're designing a network, choosing between these cables is basically a huge balancing act. Twisted pair, that's your cheapest option for sure, but it also has the lowest bandwidth, meaning it carries the least amount of data per second. Coaxial kind of sits right there in the middle for both cost and bandwidth. But then you have fiber optic. Yes, it is the most expensive by far, but the bandwidth is absolutely massive. It's moving data at literally the speed of light. Plus, it's the least affected by something called attenuation. Attenuation is really just the deterioration of a signal as it travels over a long distance. Because fiber optics are using light instead of electrical signals over copper, that signal stays crystal clear for incredibly long distances. It's the ultimate performer for major network backbones.
But of course, we don't just use cables anymore, right? We use wireless transmission, Wi-Fi, radio, microwaves. And the trade-offs between going wired or wireless involve some pretty fascinating real-world logistics. For instance, you can't just go out and broadcast whatever wireless signal you want. Those frequencies are heavily regulated by government agencies. But on the flip side of that, if you want to lay physical, underground cables, you have to get explicit permission from landowners, which is no small feat. Wireless signals definitely face way more interference, from walls, bad weather, other electronics, and yet wireless actually requires fewer physical repeaters to boost the signal across long distances compared to copper wires. Ultimately, though, for the modern mobile phone user, wireless is the only option, which makes it an absolute necessity despite all those interference headaches.
So, we've looked at single cables, local office networks, and wireless signals. But take a breath for a second and just think about the massive scale of all this. How do all these cables, switches, and signals actually manage to connect the entire world together?
Let's answer that in Section 5, the Internet's infrastructure, the global mesh. You see, the Internet isn't magic. It's actually a highly structured physical hierarchy governed by ISPs, or Internet Service Providers. It basically works in 3 steps. Step 1, right at the bottom, you have access ISPs. This is just the company you pay every month to get your house or your phone online. Step 2, those access ISPs connect upward to middle-tier regional ISPs, which exist to bridge whole cities or local networks together. And finally, Step 3, those regional ISPs plug directly into Tier 1 backbone ISPs. These are the massive, truly global networks that form the core of the Internet. They all connect to each other at these huge physical hubs known as Internet exchange points. So it's literally a continuous physical chain stretching from your living room router all the way up to the global backbone.
And sitting right at the intersections of this massive mesh of overland and undersea fiber optic cables is a really critical device, the router. A router is essentially a node on the Internet. Its one vital job is to look at a tiny packet of data, look at that incredibly complex global web of connections, and instantly choose the most efficient physical route to blast that data toward its destination. They are literally the traffic directors of the global mesh.
Now, before we wrap up, I really want to bust a major, super common misconception. People use the terms Internet and World Wide Web interchangeably all the time, but they are absolutely not the same thing. The Internet is the massive physical infrastructure we've just been talking about, the cables, the routers, the interconnected local and wide area networks. The World Wide Web, on the other hand, is simply a distributed application that runs on the Internet. Think of it this way. The Internet is the physical highway system, and the World Wide Web is just one specific fleet of delivery trucks using those highways to deliver web pages right to your browser.
The Internet is the biggest internetwork in existence. But honestly, the most staggering fact about it is that it was never designed as a single whole. There was no grand architect who drew up the blueprint for the Internet we use today. It just evolved. Piece by piece, land by land, cable by cable, it grew into this colossal, indispensable system that we rely on every single second of the day. And the crazy part? It is continuing to evolve right now. So the next time you stream a video or load a web page, ask yourself,
What invisible global pathways did that data just travel to reach the palm of your hand? Thank you so much for joining me on this explainer through the world of networking. Keep learning, keep questioning, and I'll catch you in the next one.